My name is Akbar Rhamdani. I'm a professor of sustainable metallurgy in the School of Engineering, Swinburne University of Technology. My research is in the area of high temperature processing, particularly with focus on processing of critical metals, recycling, and also decarbonization of metallurgical processes. So when we talk about green metal processing and recycling, ultimately we use our resources from Earth. So we start with something from underground, so we mine them and we turn it into what is called raw materials, such as ores, sand, rocks, wood plants, and then we further process it, we extract it, we refine it to form what is called basic materials, such as metals, chemicals, paper, cement, and fibers. We further process it to make engineering materials such as alloys, ceramics, plastics, concrete, and so on. And then we also further process it to make into products, and then we use that product. And of course, we use the products, and then at the end of the useful life of the product, we usually turn it back into the underground. So we landfill them or we burn them, right? So this is called material cycle. In the context of recycling and resource efficiency, instead of putting things back underground, we actually try to reuse this and utilize this in a number of ways. We can recycle it back to the material cycle itself, for example, to make a basic materials again. We can reuse it, part of the the product or the part there, to make a new products and also do a remanufacturing of new product. So we turn these materials and put it back into the material cycles, but not from the beginning. For example, we use end-of-life products and take the metals, and then we recover the valuable metals from it. Now, this concept is called circular economy. It is an economic system that aims at eliminating waste and the continual use of resources. However, circular economy is an ideal situation. It is an aspiration, right? We cannot really achieve 100% circular economy because actually, in every process, including recycling, remanufacturing, there's always waste generated. And from the thermodynamic perspective, there's a limit where we cannot reuse these materials anymore. So in the context of what we're talking about, it is clear that recycling is vital. So now let's talk about that in more detail. So why actually recycling is important? First of all, it actually reduces the consumption of the primary resources and also reduce the waste associated with processing these primary resources. Usually primary resources is quite a complex, and also it has quite a long process route. So if we reduce that, then and also reduce the waste associated with the processing of them. And of course, because in recycling we use alternative resources, it means that we increase the consumption of secondary resources such as end-of-life products, byproduct from industries, and other waste from our daily life. In doing more recycling, we also reduce the dispersion of toxic elements into the environment, and of course, we also reduce the space for landfilling as well. The second thing that is important in regards to recycling, recycling actually has potential to lower the energy requirements for making metals. Right? So as you can see in this table, it's showing the different energy requirement to make different basic materials, such as glass, aluminum, copper, and steel. And if we look at this one here, let's look at steel. Right? If you want to produce steel, the energy required to make steel, right, per ton of steel, is about 25 gigajoule per ton if we use primary resources. However, if we use secondary resources, if we recycle steel, we only need about 10 gigajoule per ton. Right? So that is actually a reduction of energy by 20 to 40%. And the same thing for other metals as well, such as aluminum. We can actually reduce the energy requirement by 5 to 10%, right? If we use secondary resources.
Steel is contribute to more than 7% of the greenhouse emission. So now in Australia, around 75% of the steel process is made through blast furnace and basic oxygen furnace. Then it's only 25% from EAF, and we know that with using EAF is based on scrap. So which means that we need to know how much scrap that we have in Australia, and also like the quality of the scrap in Australia.
So InfraBuild is a electric arc furnace based steelmaker. We have 2 electric arc furnaces, one in Laverton in Melbourne and one in Rooty Hill in Sydney. They use steel or scrap steel as the ferrous source, as the source of steel that goes into it. So we're very different from a blast furnace manufacturer, and because of that we naturally have an advantage because we're a lower emissions emitting process in terms of steel making. We very much understand that there are 3 major energy inputs that contribute to our emissions. The main one of those is the electricity we use to make the steel that comes out of the electric arc furnace process. The second is our use of natural gas, and the third one is our use of coke, which comes from coal that is dug out of the ground.
The other thing why recycling is important is, I also mentioned earlier before, that these secondary resources, it has some values, right? Some of them contain valuable metals. For example, if we're talking about mobile phone, if we're talking about batteries or solar panel or end-of-life magnets, right? So this is generally, we call them e-waste. Yep. So it actually contains a lot of valuable metals. Yep. And the concentration of the valuable metals in there actually higher compared to the concentration from the primary ores. Right? So it only makes sense for us to also utilize these resources and do more recycling. Right? When we're talking about e-waste, it is actually opportunity, but also a challenge. So e-waste, currently, globally, we generate about 50 million tons every year, and only about 30% actually, recovered or processed. So there's a lot of potential for us to grow and recycle these materials and get the value from this. Just to illustrate, if we're talking about a gold ring in my finger, right? It contains about 2 grams of gold, right? And these 2 grams of gold can be actually obtained from about, let's say, 15 kilograms of mobile phone waste. Right? But if you look at the primary source, the gold ore itself has got a low concentration of gold. The same amount of gold, usually we can only get it from about 500 kilograms to 1 ton of primary ores. So again, it is showing the high value and the high concentration of these selected valuable metals in the secondary resources. Another illustration, if we talk about mobile phone, right? If we talk about the share of weight in the component, right, and on elements, we'll find that 56% of mobile phone consists of plastics, right? And there's only like total, few thousand ppm of gold, silver, palladium, and other sort of exotic metals. But if we look at the value, those gold, silver, and palladium actually take about 93% value share of metals in that mobile phone. So we talk about a lot of good things about recycling. However, there's also some drawback and limitation of recycling. For example, the quantities and proportion of materials for recycling, it may not match the current demand. So we have to wait, because the time doesn't match with the production of the resources itself and the production of the new metals. The quality of recycled materials may decrease. That's the other sort of limitation. Recycling itself produces waste. So this is come back to my earlier comment regarding circular economy. We cannot really achieve 100% circular economy. Depending on the products or the materials, recycling can be expensive because first of all, we have to collect them and then transport them into their location. And then the actual processing route also can be longer. For example, if you want to extract all of the valuable metals, then it will have a longer sort of process route. The other limitation is when we talk about secondary resources and end-of-life products, there are many of them, right? So they have a different composition, they're quite complex, and to process them, it will require different processes. So that's one of the challenges, to have process that quite flexible and robust that can process different types of end-of-life products. There are a number of challenges in the current metal production and recycling processes, but one of the greatest one is the CO2 emission from these processes. For example, if we talk about iron and steel production, the global CO2 emission from this sector is about 7 to 8%. In the case of aluminum production, it's 1 to 2%. And other metal production, such as lead, zinc, copper, it contributes about 1% of CO2 emission. So that is why it is important for the optimization and also development of new processes to reduce this CO2 emission. When we are talking about developing new metals processing and recycling, we need to do it right. So we usually start with developing the process in the form of flow sheet. We analyze this flow sheet, right, using thermodynamic knowledge. And the next step after that is we're looking at the techno-economic of the process. So after that, we're also looking at the environmental impact of this process through life cycle assessment, so that we have quite an optimum process route. And this is actually an iterative process. There is a number of approaches that we can take for reducing the CO2 emission and decarbonize current and new metals recycling processes. One of the things we can do is to improve the efficiency of the process. For example, we can reduce the fuel consumption, which means that it will reduce the CO2 and other unwanted emission. We can reduce the water usage, energy, and also overall costs of the process. We can implement digitalisation, use of machine learning, AI, to optimize the process. The second thing that we can do is to use alternative non-carbon source for fuel and reductant. We can use molecular hydrogen. We can use hydrogen plasma, which is monoatomic hydrogen and also ionic hydrogen. We can use natural gas or ammonia. We can use also biomass, biochar, and biocarbon. Another way to decarbonize is to use what is called CCUS, carbon capture, utilization, and storage. In that way, we can still use the current process, but we sequestered the CO2. We can also emphasize in process innovation, developing new routes of making metals, increasing circular economy, and that is increasing recycling. All of this will contribute to the decarbonization of metallurgical industries. There are a number of novel green metals processing and recycling. In Swinburne, we are working on a number of these. For example, we are using hydrogen, molecular hydrogen, to process and recycle materials. So we use it for recycling of lithium-ion batteries. We use it for recycling alkaline batteries, and also byproducts of industrial processes, such as slags from lead production, from iron and steel production, and also for the production of iron using hydrogen, that is hydrogen iron making. The use of hydrogen means that the byproducts from the process contain water, H2O. So no CO2 involved in the process. which means that you will have low or no carbon footprint on these processes. One of the things that we are developing at the moment is to use hydrogen plasma for processing of metals. Right? Hydrogen plasma is ionized form of hydrogen, such as monoatomic hydrogen and ionic hydrogen, H+. Now, why this is useful? Because it has quite a strong thermodynamic potential. It can actually be used to reduce stable oxides, such as alumina, calcia, titania, and also rare earth oxide. To produce hydrogen plasma, we need a bit of energy to break the hydrogen bond for them to be able to be used for the reduction. In Swinburne, we are developing what is called Swin H2 Plus plasma reactor. It is a novel hydrogen plasma reactor where we use plasma torch of 35 kilowatt power, and we combine it with a 3D printed copper shroud and also reactor tube. And this can be used for processing of materials with a flow rate of 50 grams per minute. We have demonstrated this for production of iron from iron ore and also processing of silica and other slag materials. This shows the product of the process where you can see it contains 100% of iron that is reduced from the initial ore. The other process that we are developing in Swinburne is through metallothermic reduction. In this case, we are using metals as a reductant instead of carbon. Similarly, we are not producing CO2 in the process, hence low carbon or no carbon processes.
My specialist is in the battery recycling. Right now, I'm focusing on lithium-ion battery recycling, trying to take out valuable metals from this waste. So the battery recycling has a lot of important aspects on it. The first one is that we want to reduce the growing accumulation of end-of-life batteries. So these batteries coming out from the electric vehicles, from your phone, laptop, tablets, and etc. And secondly, by doing recycling, it enables us to recover critical materials. And these materials are really essential for the national supply chains and also the technological advancement. So we're in the high temperature laboratory, and this is horizontal tube furnace, one of the high temperature furnace that we use to process our end-of-life batteries. So these are the samples. This is coming from spent batteries that has been processed, such as dismantling, grinding, crushing, and a lot of washing, chemically washed. So this is called black mass, and it contains a lot of cathode and anode materials, and it also contains a lot of critical materials in it. So what we need to prepare before we put in the furnace is that we need to press this powder with these pressing tools, and it will come out as a black mass pellets. So we then insert these pellets into a sample holder and put it in the high temperature furnace. So I'm going to explain a little bit of the components of the furnace. So in the middle zone here, we have heating elements. So this zone is the area where the sample needs to sit and to receive the maximum of heat. And this cylindrical tube is made of alumina, and this part on the both ends are called flanges. This is for sealing the furnace so that we don't have a lot of oxygen coming out from the air, so that our environment for the sample is protected. And in the other hand of the furnace is where we insert the sample. We also call these flanges. And in these flanges, we have a lot of inlets. Can be 2 or 3 inlets. One is for the gas. In this case, we use argon or nitrogen for the inert gas. So this gas is not reactive, so it just keeps the sample really protected. And the other inlet can be for the vacuum purposes. So we insert another hose connected to a pump so that we can have really low pressure for reductive environment. So the purpose of inserting this sample into the furnace is that we want to separate the lithium from the cobalt, because lithium and cobalt are the critical materials. So by exposing this sample into high temperatures, we want to take out the oxygen by the help of reducing agent or aluminum. So aluminum will take out the oxygen and make alumina, so that it will leave out the lithium and cobalt, and we can separate those two metals from oxygens. So the way we insert the sample is we just put the samples sitting on the top of the bowl, and then we can just insert it from this end of flanges. And there is a mechanism here made of magnet, which is connected to our sample holder. So when we slide it in, our sample is just going to slide through the middle zone of our furnace. And we wait for certain period of time for holding time. And from this experiment, we take out the samples and we prepare the sample to be looked at characterization tools such as SEM, EDX, and XID.
This process typically generates heat. It's an exothermic process, and then we can use this heat as part of the process. So in terms of energy requirement, it also reduces the energy requirement. So we usually use metallothermic reduction if the metals to be produced are more valuable, or the source of metal reductants are readily available. For example, we can use waste as a source of metal reductant. So in the recycling of lithium-ion batteries, we are using aluminum and react aluminum with the cathode materials to produce lithium, cobalt, and other metals in the battery, end-of-life batteries. As you can see, this is the metal that we produce, cobalt, aluminum alloy, as well as lithium in the gas phase, where, after condensation, we recover it from the cold finger.
My name is Reza Muklis. I'm a lecturer in mechanical and product design engineering. Now I'm working more on the recycling of the metals, and also with the green process of the metals. How to produce the metal with minimum carbon footprint. So related with the plasma things, we also try to produce silicon. Silicon is, we know that it is one of the critical mineral in Australia, and that silicon we also use the hydrogen. Usually silicon is produced through the reduction by using carbon. So now we're trying by use the hydrogen plasma. And one of the source of the silicon that we use is rice hull. Australia produce around 100 million kilogram of rice annually, and 20% of it is hull, which is just disposed, either as a landfill, or maybe it's just as a low value product, like for the bedding for the animal. So the thing is, with the rice hull, it have like a high, quite a high purity of silicon, because they have like a selective intake from the plant. So then we use that rice hull to try to extract the silicon out of it.
So in conclusion, metal recycling is a cornerstone of green metallurgy and decarbonization. It helped us in reducing greenhouse gas emission. It helped us with conserve resources, and also support the transition to a circular and low carbon economy. Obviously, new innovation in green metals production and recycling are needed. And for us to be able to do this, we need the collaboration from different stakeholders.